Hello guys, my name is Aleph Figueiredo. I'm a master's student from the Structures Engineering Department at the Federal University of Minas Gerais, and I'm going to present the paper entitled A Machine Learning-Based Constitutive Model for Nonlinear Analysis via Finite Element Method. The authors of this work are, besides me, doctoral students Saulo Castro and Samir Saliba, and Professor Roque Pitangueira. This work is divided into 5 main topics. I will talk a little about each one throughout the presentation. We are living the fourth industrial revolution, also known as 4.0 industry. The 4.0 industry has been transforming the world through technological innovations. In this context, artificial intelligence stands out. AI is a set of techniques used to make a system simulate human intelligence through the ability to correctly interpret external data, to learn from the data, to store acquired knowledge, and to use this learning as a decision-making mechanism. The algorithm that allows the system to learn automatically by previous experiences is known as machine learning. The most applied technique of machine learning, and the one used in this work, is the neural networks. Neural networks are computational models inspired by the biological structures of neurons and the internal operation of the human brain. A multilayer perceptron is a neural network model able to approximate nonlinear functions and therefore known as a class of universal approximators. A neural network-based constitutive model is a multilayer perceptron that is able to represent the behavior of a material in a structure. The first figure shows the aspects of a biological neuron of the human brain. Neural networks are a nonlinear dynamic system formed by a large number of neurons highly interconnected. A multilayer perceptron consists of an input layer of neurons, one or more hiding layers, and an output layer. Then it's observed the structures of an artificial neuron. Inside an artificial neuron happens the linear combination described by equation 1. Each neuron receives input data X through its connections, which are weighted by their respective synaptic weights W and added together along a bias B. This value is known as induced local field V that passes throughout a nonlinear activation function and results in the output signal of the neuron. So, the learning rule applied in a multilayer perceptron is a supervised learning process named backpropagation algorithm. In a supervised learning, each example of the training database represents an input signal and a corresponding expected answer as an output signal, that is, used to compare the current result of the network with the desired one, and then calculate an error signal that it will be responsible for the modification of the synaptic weights. This method has as main object to minimize the synaptic weight vector W in order to find the vector that best correlates the network output values and the target values for these outputs through an unconstrained optimization technique known as gradient descent. The training of a neural network happens through an iterative process which involves the propagation of the training set and the adjustments of the synaptic weights. The training technique used in this work was k-fold cross-validation. A neural network-based constitutive model is developed through the training of a multilayer perceptron with the backpropagation learning algorithm on the stress-strain results from experiments or from numerical simulations. The figure shown above illustrates this model. The input data of the network are a state of stresses, a state of strains, an incremental state of strains, and also historical parameters. The network output is the incremental state of stresses corresponding to the incremental state of strains. For nonlinear materials such as concrete, the historical parameters used are previous stress-strain states. In order to develop a neural network-based constitutive model, it was used a multilayer perceptron model from a machine learning library for programming in Python known as scikit-learn. The network presented by equation 3 was proposed to represent the constitutive model of a plane state stress problem of a concrete structure. First, a nonlinear finite element analysis of a L-shaped panel with a thickness of 100 mm and a vertical load depth of 7 kN was performed as shown in the figure above. Then the model was discretized as shown in the following figure. To solve the system of nonlinear equations was used the Newton-Raphson process with the direct displacement control method and the Mazars scalar damage model for the parameters shown above. The following figure shows that the equilibrium path of the monitored point was close to the experimental curve of Winkler 2004, and therefore it would be reasonable to use the results of this material's behavior in the structure as training data for our network. Therefore, the network was tested to predict the history of the integration points of the elements whose information wasn't used in the training. The figure above presents the global stress-strain history for the element 100. The following figure presents the local stress-strain history for the element 394, both showing the multilayer perceptron performance compared with finite element results. It can be observed that there was a satisfactory agreement between the curves obtained through the finite element method and the curves obtained through the multilayer perceptron. The network was able to learn precisely the unload situation of the former element and the softening behavior of the later. After that, the same neural network constitutive model was used to predict the stress status at the integration points of a three-point bending test model with the same Mazars constitutive properties. The problem is presented in the figure above. The beam has a thickness of 50 mm and is subjected to a central load F of 0.8 kN. The following figure shows the local stress-strain state at the integration points of the element 516. This element is located at the tip of the crack and is under tension. Once again, the multilayer perceptron was able to predict with great accuracy the stress history of the current element, but now in a different structure. Finally, 1000 stress-strain states of the finite element mesh were randomly chosen throughout the nonlinear analysis, and then the multilayer perceptron was used to predict the stress values in order to verify the network predictive capacity for data on the entire structure. As we can see in the figure above, once again, there was an excellent agreement in the results between the multilayer perceptron and the finite element method. To conclude, it's important to note that the experiment showed the great ability of the multilayer perceptron to learn a constitutive model, and is very promising as a tool to develop more general constitutive models. However, the same multilayer perceptron wouldn't be able to predict the behavior of another material type unless trained with representative data of this material. Besides that, it's important to point out that the model was tested with a fixed material in problems of different geometries, but commanded by predominant states of tension. This work is just the first experiment in a larger research and with broader ambitions. I would like to thank everyone present here, the Federal University of Minas Gerais, the postgraduate program in structural engineering, and the research development agencies.